All right, last lesson for this unit on solutions, and we saved the best for last. Last topic we were talking about, last video, we were talking about electrolytes and non-electrolytes, and it's important to kind of go back again really quickly and take a look at what we were talking about before, and just quickly, a very quick review here because this is going to be a little bit of a challenge to stay with it. Again, we're looking at your acids, your bases, and your salts as your electrolytes because they're going to break up into ions. Here's some good examples. And again, the total number of particles is what we're looking for here in the formula. However, in the non-electrolytes, we're going to not break up at all because those molecules stay together. So the key is the fact that these non-electrolytes, you have to recognize them first. They're going to stay as one. But your ionic compounds or your acids and your bases will break up into the number of ions here. Now, why do we really want to know about this and why do we care? Well, there's something called colligative properties, and that's really the subject for today. And the colligative property, it's a strange word. It's a strange name, but what simply colligative comes from the word collective. All right, so colligative properties of solutions are going to really depend on the number of particles, the number of solute particles. Now, these particles could be molecules or ions, okay, relative to solvent, okay, but not upon the identity of the solute. So you really eventually want to take a look at the number of particles total at the end. Again, we talked about non-electrolytes breaking into one particle per mole and electrolytes breaking into more particles, but it's the end result, it's the number of particles that we're interested. Okay, now there's a few different types of colligative properties. Those colligative properties will include the boiling point, which will be elevated, and the freezing point, which will be depressed or will have gone down. Okay, and there's a few others. Okay, solute particles from the attractions to the solvent are going to interrupt the normal phase change behavior of the solid solvent, and because of that, it's not going to boil and freeze like it normally would if the solute wasn't there. Okay, so there's a little bit here. All right, so again, just to repeat that, it's really important to know that we're dependent on the total amount of particles, the number of the particles, not really what the particle is. All right, and we're going to see that as we move through this. Okay, so just let's start from the beginning. If we have pure water, we know in pure water that you're going to boil at 100. So that would be a boiling at 100 degrees Celsius. And the normal freezing point would be at 0. We know that's true for pure water. Now, as you add solute to this, okay, as you add solute, what we're going to find is that the temperature that would normally boil at would be 100 would actually become higher as you add more solute. So as the solute begins to increase its concentration for higher concentrations, your boiling point would go up. Let's just say to maybe 102 here. I'm just making an example. Or maybe you'd freeze at -5, okay, instead of freezing at 0. So what you're really doing is you're expanding that liquid range of the water. So instead of the water having this range of 0 to 100, now it would have a liquid range of -5 below 0 all the way up to 102. Okay, and that could be useful for a few things. All right, but again, that's dependent on how much solute you add. More solute added, the bigger the change. All right, so a couple things you want to realize. So we call that boiling point elevation. We call it freezing point depression. You would have a lower freezing point and a higher boiling point. And again, as you add the solute more and more, this will be elevated and depressed. Okay, so a couple of things you want to keep in mind qualitatively about this. Again, we haven't done this qualitatively. We're going to do this quantitatively next. Okay, the more solute you add, the larger the boiling point and the freezing point change. Okay, electrolytes are going to have a larger effect. So this gets a little more specific because for the same amount of concentration, they break up into more particles. Okay, all right, and we're going to see that in a minute. So for example, sodium chloride would break up into 2 particles, where glucose C6H12O6, okay, is only going to break up into 1 particle. So if you had 1 mole of this, you'd get 2 ions. You get 1 mole of this, you'd get 1 ion. So again, the number of particles here is what we want to pay attention to. Okay. Now, so how do we actually use this? Well, salt on the roads in the winter, what we do is we add salt. That salt breaks into ions. It attracts to the water molecules in the ice, okay, in the snow, okay, and begins to melt the ice by lowering that freezing point. That freezing point is lowered, okay? that begins to form liquid water, and now we can lower that freezing point, and water will be a liquid below what we want it to be, which is important for keeping those roads clean. Okay, antifreeze in cars. Okay, we expand that liquid range so water can absorb more heat in an engine. Okay, so that's important to know. And antifreeze is typically an alcohol. Okay, we use a high concentration alcohol. We use a very strong concentration, which has a lot of particles into it. Okay, and we can also use the same idea, antifreeze kind of into solutions to spray on the wings of an airplane to keep the ice from reforming on the wings. So again, some uses that we could use this for. All right. All right. So what we want to do is qualitatively express how much does that boiling point or that freezing point go up. Okay, and that's an interesting point on this. Okay, and to do this, we need to define a different type of concentration. Okay, and we've talked about molarity. Molarity was an important one because we talked about how many moles there were per liter. And again, when we're talking about the number of particles being important, molarity is a very good idea. However, there's a problem with this. Okay, when taking sensitive temperature data, using molarity, which is moles per liter, okay, is not ideal because the volume of solutions will change slightly with temperature. So when we're talking about heating and cooling something, we don't really want the molarity to change, right? We know that the moles don't change because the number of particles don't change with temperature, but we know that liquids can expand or contract slightly with temperature. So in a cold liquid versus a hot liquid would take up more volume. So that means that the liters would change. And we don't want to really do that. We don't want a concentration that's changing all the time with temperature. We want to choose a better measurement that is temperature independent. So what we do is we alter this slightly. And instead of using the term molarity, we use the term molality. So I know this is probably driving you crazy, and it does drive people crazy because it's so close in the way they spell it, and it's even closer in how they calculate this, but you got to accept that. And we're going to use this little italicized M for molality. You will only use molality for when you calculate boiling point and freezing point changes. Okay, other than that, you would use molarity all the time. Okay, so now how do we use molality? We simply say the number of moles of solute, very similar to molarity. Okay, but instead of using liters of solution, we're going to use the mass of the solute, specifically in kilograms. Okay, so we would take the molality now as the moles of solute in the kilograms of solvent. Okay, and the unit will be moles per kilogram, or it will be this italicized M. And again, we're going to have to be careful that we may need to convert grams into moles and out of the mole. Okay, we've done that before, right? Grams to moles. Okay, and we may need to convert grams to kilograms. And again, remember, when we're going grams to moles, we're going to divide by the GFM. Okay, when we're going moles to grams, we're going to multiply by the GFM. Okay, and again, same thing. If we're going grams to kilograms, we're going to divide by 1,000. If we're going from kilograms to grams, we're going to multiply by 1,000. All right, so we're going to keep that in mind as we go. Again, kilograms of solvent, not solution. Okay, so we have to make sure we change to kilograms. Okay, and in this case, we make sure that we're using moles of solute. All right, so quick question down here just to run through molality really quickly. A quick molality question is, let's just say I have 1.8 grams of glucose and I'm dissolving that 50 grams of water. Again, this is your solvent. We're going to need that, right? Okay, and if I have that, okay, I'm going to say that the molality, a little italicized M, is equal to the moles of solute, okay, over the kilograms of solvent. Okay, I have to find the moles of solute, so I'm going to take 1.8 grams divided by the GFM of glucose, which is going to be 180 grams per mole. You could take the time to do that on your own. Grams per mole. Okay, and I'm going to get 0.01 moles, okay, of that. Okay, and now I also have 50 grams of this divided by 1,000 kilograms, 1,000 grams per kilogram. I'm going to get 0.050 kilograms. Okay, so I take moles per kilogram. I got that divided by that, and I get 0.2, a little italicized M, or moles per kilogram. That becomes my molality. Okay. Now again, what am I? That's fine. And that's kind of easy. It would be just as easy if you did a molarity formula. But like, okay, what's the big deal? How does this really affect anything? All right, how does this really affect what I'm going to do? Okay, and that has to do with the next part. So you're going to need to be able to find the molality. Now, what do we use it for? Okay, now it becomes interesting. Okay, now after you add solute to a solvent, okay, you want to then calculate the new boiling point and freezing point, which is going to depend on a couple of things. Okay, number one, it depends on the concentration of or the molality. How much sugar or salt or thing are you actually putting in there? So it depends on that concentration. And number two, it depends on the number of particles you break up into. So last video, we talked about breaking up the particles. You want to determine how many particles you're breaking up. Okay. If you have these two pieces of data, you then can calculate the change in the boiling point or the freezing point. Okay. So to calculate the change in boiling point, okay, the change in the boiling point, this is not the new boiling point, but the change in boiling point is going to be a special constant. Okay. Now this is going to be a constant that's only for liquid water. Okay, so we're going to have this memorize. We're going to memorize 0.52 times the molality times the number of particles in that formula. Okay, and when you multiply these together, you get this little formula. So there's your 0.52, there's the molality in M, and here's the number of particles. So also notice that you'll cancel out your molality and you'll be left in Celsius. This is a counting unit, has no units. All right, so you're going to have to find from the formula, okay, from the formula on how you're going to do this. And you simply multiply them together, and you'll get the change in the boiling point. Now, if you want to find the new boiling point, you're just going to take 100, because you're going to be dealing with water, plus whatever that change is, okay? And remember, that boiling point is going to increase, so that number will be higher than 100. All right, so that's to calculate the boiling point. To repeat, you're going to take 0.52 for liquid water, times the molality that you're going to calculate, times the number of particles. Now this, again, you're going to have to find this number of particles from the formula. If you don't know your formulas, this is going to be a little bit of trouble for you. So you want to identify your formulas. Okay? Now to calculate the freezing point, it's very similar, except that instead of using 0.52, we're going to use 1.86, and everything else remains the same. Times the molality, times the number of particles present. And again, you would then have, so again, you really want to know this formula, okay? And you want to know this formula. So the freezing point, the change in the freezing point will be 1.86 Celsius per molal, okay? Times the molality times I. Again, you're going to find I from your formula, okay? And again, a little bit differently here. Remember, the new freezing point is going to be below zero, so we're going to have to subtract this change. Remember, the freezing point is going to decrease. Remember, boiling point goes up, freezing point goes down. Right? The BP goes up, the FP goes down. So you can subtract it from zero. So really, this is what we're doing. All right. So I know it's a lot being thrown at you here. We're gonna just take a little bit of time to get this together, but it's not that big of a topic. There's just a lot here. All right. So let's do a quick problem. All right. Again, before we even finish this, okay, just remember that the constants 0.52 and 1.86 are for water only. I would say for liquid water only. Other solvents will have different constants. Okay, and these are going to be found by experiment, okay? And if they're in a problem, they're going to be given to you, so you don't have to worry about that. All right, so let's do a quick problem. Let's just say a student in a lab dissolves 179 grams, okay, of magnesium chloride. Give myself some room here. So 179 grams of magnesium chloride into a liter of water. What is the freezing point of the solution? Now, we know that it was pure water. Okay, if it was pure water, we would be, zero. We would be 0 Celsius, right? Because in pure water, water would freeze at 0. But you're adding this all the solute. Okay, so really quickly, let's just examine magnesium chloride, and we know this is ionic. We know this is ionic, and magnesium chloride would have 3 total ions, right? We break them into magnesium chloride, magnesium plus chloride, and there would be 2 chloride ions, right? So remember, you're breaking ionic compounds into this. So here you have 3 ions. So there's your I value. Your I value is 3. Okay, so we have that. So we have that piece of information. Okay, so we know that the changing freezing point is going to be equal to 1.86, okay, times the molality, times I, and we already know the I. Okay, so that's easy because we identified this as becoming ionic. So really all we got to do is find the molality. So we know the molality equals the moles over the kilograms of solvent. All right. So again, we're given grams. So again, we got to do that. So 179 grams, okay, of magnesium chloride, MgCl2. I'm going to divide that by 95, which is my grams per mole, my GFM. Okay, again, you can do that quickly here. GFM is 95. Okay, so I am going to have a grand total of here. I am going to have, if I do that, I'm going to get 1.88 moles. Okay, so that's my first step. Okay, my second step now is I'm going to take 1.88 moles. Okay, and I'm going to find the molality by dividing by my 1 liter of water. Now, 1 liter of water is the same as 1 kilogram of water, just like 1 milliliter is the same as 1 gram. So water can be converted right to kilograms if it's in liters. So this would be 1 kg of water. Okay, would give me a molality of 1.88 molality. So we got what we need. We got what we need. All right, so this is easy. I'm just going to take now in step 3, I'm going to take my change in freezing point is going to be equal to 1.86 times 1.88 molar. Okay, and I'm going to times that by my ions 3. And I'm going to get 10.5 degrees Celsius. Okay, which is my change in the freezing point, which means it's going to go down from 0. All right, so I'm going to take my new FP is equal to 0 Celsius minus 10.5 Celsius. Okay, so my answer is negative 10.5 degrees Celsius. And that becomes my final answer. So we could see that this would freeze below 0, this salt solution. Okay, so really important that you know that. Again, that would be the answer on that. I'll pause really quickly and I'll give you the answers to the next 2 questions. You should do those on your own and complete them. All right, so that you know how to do this. Yes, you will have a question like this on your test next week. All right, but I will simply give you 1 question. I will not make this too crazy, but you need to know it nonetheless. All right, so if I go to the next 2 questions and I erase this here for now, you can always go back and check it. Okay, the answer to this question, if you do this question, will be 100.3 degrees Celsius if you round. Okay, the answer to that one. And the answer to this one down here, I know I'm not giving you a lot of room on the PowerPoint here, but the new freezing point, the answer to this would be, the boiling point would be 101.88 Celsius. And number 2, the new freezing point would be minus 6.73 degrees Celsius. Okay, so those are the answers to the next 2 practice questions. Yes, you should do them. Again, if you need to go back over and watch this again, that would be a good thing. And then you can have some practice within the thing. I would say the biggest thing, guys, here is recognizing your compounds. If you can recognize your compounds, then this thing becomes a little bit more bearable to do. All right, so that becomes it. And enjoy. Have a great day.